Hello and welcome back to my course Amiga Hardware Programming in C. In this episode I will introduce two additional features of the Blitter: area fill and line draw. We will be building on the things that were introduced in episode 5, so if you haven't watched that yet, I would recommend doing so first. When I am talking about an area fill, I mean that we start with a defined graphical outline such as a polygon and then fill that with a solid color. Setting up an area fill is actually pretty easy. It can be an optional stage in the Blitter copy operation where the first stage is shifts, masks and combining, which generate an intermediary result that is passed to the area fill stage to obtain the final result. In addition to the typical parameters needed for the blit operation, we also need to enable a couple of bits in the blitcon register. Since area fill only works in descending mode, we need to make sure that the descending mode bit is always set. Then there are two bits that specify that we actually want to perform an area fill, and those are the exclusive fill enable bit and the inclusive fill enable bit. Depending on our needs, we set either one or the other. The fill carry input bit is another parameter that controls how the area will be filled. I've prepared a couple of animations to help understand how area fill works. In each case, we will only look at a small section of a line in the blit area. Imagine the Blitter had a pen for filling areas, and there is a status bit called the fill carry bit, which determines the state of that pen, where a 0 means the pen is up and won't draw anything, and a 1 means the pen is down and will draw. We can tell the Blitter to start filling at each new line with either the pen up or down by clearing or setting the fill carry input bit in blitcon 1. Let's start with a line with 2 bits set to limit our fill area. The fill carry bit is initially 0, and so the Blitter works its way from right to the left until it sees the first 1 bit. As soon as it sees that bit, the fill carry bit state will switch to 1 and will start setting bits until it sees the second set bit, where it will revert to a 0 and continue to the beginning of the line. In the second case, we start just like in the first example with 2 bits as the area limits, but the fill carry input bit is set to a 1, which means the pen is initially down. So the Blitter will keep setting bits until it finds the first area limit bit, where it switches its state to a 0 and moves ahead until it finds the second area limit bit, where it reverts to a 1 and will continue setting bits until the beginning of the line. Maybe a somewhat unexpected effect that I observed is that the first bit in the line will be empty in inclusive fill mode while it is set in exclusive fill mode. Now what happens if we have an odd number of limit bits in the line that we want to fill? In this example we have 3 area limit bits set, so the fill carry bit flips 3 times, resulting in the pen down state, and will keep filling until the beginning of the line. And what happens if we use the configuration we saw in the first example, but fill in exclusive mode? In that case, it will fill the area between the 2 area limit bits, but will clear the second limit bit, resulting in a filled area that is 1 bit narrower than in inclusive mode. I've prepared a small example program that you can use as a starting point for your own area fill experiments. Essentially, these are a couple of lines that serve as the fill area limits on a 64 by 64 pixel grid to see the extent of the fills. You can find the image in the source code folder, and as usual, it was converted using my maketiles utility. I defined a small structure that holds the parameters for the fill function that we will see in a moment. It has the top left and bottom right corners of the blit window and the fill parameters. Then I defined an array of these parameters for each of the 8 shapes in the image that we are using. The input handler fills one of these shapes whenever the user hits the spacebar. This is our fill function. It essentially copies an area of the source image to itself in descending mode. Normally this would have no visual effect, but since we activate area fill, the Blitter will fill in the space between the fill limits. There are no shifts or masks, so instead we use the top left and bottom right corners to determine the blit size rounded to their nearest word boundaries. Then we set the bits for fill mode and fill carry input. The remaining parameters are just as they would be in a descending copy operation. Alright, Now I will just quickly show you what you are going to see when you run this example program. Let's talk about line draw, another well-known feature of the Blitter. The drawing method is based on the Bresenham algorithm, which has the advantage that it's entirely based on integer operations and is very efficient. One of its main properties is that we use the two endpoints of the line to determine an octant and then perform rendering based on the value of a decision variable. I will now briefly introduce the concepts behind the Bresenham algorithm so you get an idea why the Blitter is initialized in a particular way. This is a pseudocode implementation that only works for one octant. In this example, we want to draw a line between the endpoint x1, y1 and x2, y2. Using these, we can calculate the values dx and dy, as well as d_o and d_no, as well as an initial value for the decision variable d. The algorithm works such that we initially set x and y to x1 and y1, increment x within a loop, and increment y whenever the decision variable is greater 0. We update the decision variable d depending on whether it is greater 0 or not, and draw a pixel at position x, y in every iteration until x becomes x2. Let's assume we want to draw a line between endpoints p1 and p2, and the origin is at the top left corner of the bit plane we want to draw to. From these endpoints, we calculate the values dx and dy, which are the absolute differences between x2 and x1 and y2 and y1. The crucial switch for activating line mode is bit 0 in BlitCon 1. Once it is enabled, many of the Blitter registers will actually change their roles. We will first look at the octant code. These are bits 2, 3 and 4 of the BlitCon 1 register. Their names are sometimes up or down, sometimes up or left, or always up or left. And now you can pretend I've never told you about that because it really doesn't matter. What does matter is that these 3 bits form a code combination that corresponds to a specific octant. For this, we place one of the endpoints at the center of a coordinate system and split that coordinate system into 8 equally sized sections. Here is a table that shows which code combinations correspond to each octant. Which octant we use depends on the position of the other endpoint. With 3 comparisons, we can decide which octant the line should be drawn in and use the corresponding code in the table. Okay, now that we have established the octant code, we can set the other values that we need in order to draw the line. We have already calculated the values dx and dy, so next we determine which one of those is the smaller and which one is the larger one. And let's call these values dmin and dmax. With these, you can set the register split A pointer, blit A mod and blit B mod to the values you see on the screen. Remember when I was introducing the Bresenham algorithm? These values correspond to the initial decision variable and the d_no and d_o values, but with a factor of 2 and adapted to the octant that we are drawing to. Next, we specify the destination area. For this, we set the word address the first pixel of our line is located at into the blit C pointer and blit D pointer registers, and the width of the bit plane into the blit C mod and blit D mod registers. You might wonder why we have to specify the destination twice, and it seems like that the hardware reference manual does not explain that. It turns out that blit D pointer only applies to the first pixel of the line, and we could point that register to some empty memory so that the first pixel does not get drawn. There are cases where this could make sense, and there are various online discussions you can consult if you want to know more about that. Now let's look at the registers that affect the appearance of the line. Bit 15 of the blit ADAT register is set to 1. We could imagine that this is our line drawing pen, which moves from left to right while it sets the pixels of the line. The blit BDAT register serves as the pattern register. Imagine that while the pen in blit ADAT moves from left to right, it will perform a bitwise AND with the bit in blit BDAT in the same position. If we want a continuous line, we should set all bits to 1, otherwise we can define any pattern of zeros and ones here. At last, we should set all the bits in blit A FWM and blit A LWM to 1. Now let's take a look at the final set of registers that we need. We have already set the word address of the line's first pixel into the blit C pointer and blit D pointer registers, and we set the pixel position within that word into the blit_con zeros upper 4 bits. Bits 8, 9 and 11 always have to be set so that DMA channels A, C and D are enabled while channel B is disabled. The LF byte offers some room for experimentation. As a starting point, we can use the Hardware Reference Manual's recommendations for XOR and cookie cutter mode. When we use XOR mode, we get the nice effect that we can erase a line by drawing it a second time using the same parameters. As we've seen before, the blit_con1 register contains the line mode enable bit as well as the octant code bits. Furthermore, we have to set the sign bit when the value we calculated for blit A pointer was negative. At last, with the upper 4 bits, we set the position of the line pattern. Typically, we would just set it to the position of the first pixel of the line, which is stored in blit_con 0, but feel free to experiment. An interesting function is activated with the single pixel enable bit. This forces the blitter to only draw a single pixel per vertical position. This makes it possible to draw border polygons that can then be filled with the area fill function. Finally, as with any blitter operation, we write the blit size register last to start the line draw. Bit 1 always has to be 1, and the upper 10 bits are set to the value dmax plus 1. Of course, I've prepared an example program, and it is very similar to the area fill example with the difference that we now have a drawLine function. It does everything that we discussed, so please change the parameters to your liking and see what they do. So here is how that looks like in UAE. I've set up a few examples like colored and patterned lines, and the last one demonstrated erasing a line with XOR mode. Now that we have seen how to draw lines and fill areas, it's time to put these two concepts together to create filled polygons. And the simplest polygon would be a triangle. In principle, this is straightforward. We draw lines in single pixel mode to connect the 3 corners of a triangle and then apply area fill. However, that means for multicolored triangles, we would have to perform 4 blitter operations for each bit plane we want to draw to. If we draw many triangles, this will be too costly. Furthermore, due to the way that area fill works, we can't just draw into an image that already contains data, since that would lead to unexpected fill results. We can solve this by first drawing our triangle into a scratch bit plane and then blitting it into the target bit planes using a cookie cutter operation. There is another issue you will likely encounter. You see that in the first example. The triangle is filled incorrectly, while in the second example it looks like expected. That's because the first triangle has a rendering error that leads to one of the bottom line's pixel being on the same line as the endpoint. In the second outline, the bottom line was drawn in a different direction, so the problem did not occur. Here I have followed the recommendations from Scali's blog, which essentially say to always draw from top to bottom in XOR mode and to omit the first pixel. I am not going into the details of example program 3 since we already covered the individual parts. The first square serves as our hypothetical image buffer, and the other squares are our scratch buffers that are used to draw different colored triangles. The concepts introduced here can only serve as a starting point for writing line and polygon-based programs. Now it is your turn to breathe life into it. I included a few links in the description if you want to know more about this topic. Do you have any questions or remarks? Let me know in the comments. Please consider subscribing and activate notifications so you don't miss when I publish new content. Thanks for stopping by and take care.